of the information, and also provides location transparency, which means that you can exercise control from any place on a network. This is completely independent of the fact that you might not actually be connected to that piece of the forwarding plane or data plane. So one place you exercise control, somewhere else something happens, and the application does not necessarily need to be aware of whether the place that it's exercising from is actually where the work happens. The node in our some of the functionality that we've added recently is that in order to accommodate changing workloads and changing sizes in the environment, the cluster itself can be dynamically extended or shrunk depending on needs. Now, that's just as a sort of overall view of the cluster. Now, clearly, in order to provide centralized view of the information, we have to now figure out how we're going to treat that information. In our view, based on our first-hand experience with prior prototypes of ONOS, we decided to treat the information differently depending on what kind of information it is. For the most part, it can be said that information coming from the user, the control commands coming from the user or for some control entity outside of ONOS, heading towards the environment, is treated in a strongly consistent fashion. It's important for things like flows to the degree on what we're putting down on a forwarding plane. It's important that we also make reservations for, let's say, lambdas on optical network, that those occur, the allocations of those occur in a consistent manner. So most of the information from the north to the south is treated in strongly consistent fashion. Whereas all of the information coming from the environment, telemetry and sensory data going to the north, that we generally treat in a very loosely consistent fashion, eventually consistent actually. Because you know, if I turn off the lights in the room, some of us might be blinking at the time the lights go off, and so we might actually not notice all at the same time that the lights went off. But it's not important that we agree with each other that the lights are off at that instant moment. It's better that we agree eventually, and then some of us can react to the fact that lights went off faster than if we were to wait for consensus. So that philosophy governs that approach. Now, rather than thinking, rather than thinking of the state of the network information base that ONOS keeps as a single monolithic database, rather than thinking of it this way, ONOS looks at the core as sort of a set of abstract stores, each of which treats the information in accordance with the nature of the information, based on where it mutates, where does it mutate at the north, does it mutate at the south. So, topology information such as devices, links, and hosts is treated in a loosely consistent fashion. Device mastership code has to be treated in a strongly consistent fashion. You get the picture. So these abstract logical stores are, of course, high-level abstractions, but they themselves are built on a set of low-level primitives. And the set of primitives that are available in ONOS has grown considerably over time from our first release. And these are just some examples of the most, I guess, popular ones. Such as eventually consistent map or consistent map and so forth. So the programmers here will immediately recognize similarities to a lot of the primitives that are in Java. And as a matter of fact, a lot of these structures can be projected as those familiar structures in Java. Where that becomes very useful, that familiarity, is because these same primitives are made available for applications to develop their own stores. Why is this important? Because if we develop, in order for ONOS as a solution to be highly available, scalable, and performant, it's not enough for the core to be that. The applications on top of it have to also be that. Because otherwise what's the use? If the valuable information that application keeps becomes compromised or does not scale, then the overall solution doesn't scale or is not resilient. So that's why these distributed primitives are actually offered as part of the SDK that ONOS supplies. It should be also noted that ONOS clustering uses a single messaging substrate. This specific port by default, of course, you can change it if you want through configuration. It's very easy, but by default it uses this port. This also makes it easy not only for deployments and configuration of any firewalls that may exist between nodes, but also for securing the communications. If you need to secure them through HTTPS or through TLS. So I already alluded to this, the high-level distributed stores. This is an example of sort of strategies that they use. So all of the topology is based on eventually consistent map. Device mastership is based on leadership primitive. Flow rules, on the other hand, are based on primary backup replication strategy, where the master, the current master of the device, holds the sort of the authoritative copy of the flow table, and makes sure that there is at least one backup out in the cluster that holds a copy of this table in case something happens to the master. Intents are treated in a strongly consistent fashion. Again, an example of information coming from the north to the south, consistent. This is also consistent. It just does not necessarily, it just uses a primary backup strategy. Same thing for network configuration, for device key management. Those are examples of consistent map. As a matter of fact, one of the things, application state was eventually treated in a loosely consistent fashion, and we actually discovered there were some corner cases that led to issues. And this slide is slightly out of date. We've actually migrated the applications to be backed by a consistent state, fully consistent state. Yeah. So there's just some examples. So the examples of the services and subsystems within the core, what kind of stores they're accompanied with, and what primitives they use. But of course, application stores can also use this, as I alluded to earlier. So we have some examples already of applications today that build their own stores using the available toolset. And these are just some of them. And clearly the list is much longer than that, but these are just some popular ones. So now we're gonna start diving a little bit more into the detail. So we're gonna cover some of the same information that I've already talked about, but hopefully in more detail. So the idea here is, so what is the right model for SDN? That really depends on what the right model is for the particular state. We talk about topology, flows, flow statistics, how those are treated. And so generally, so again, this is sort of a reiteration of the philosophy that I talked about. Source of truth depends on where the source of truth lies. For it lies in data plane versus it lies in a control plane. So in case of topology, let's see if you were to look at topology, right? The idea here is that it needs to that the mental picture that the controller has to be reasonably accurate in correspondence with the actual environment, what's in the environment. So it's really definitely important that that it is accurate, but it's not necessarily important that it is that all the controllers agree at any given time on what it is. As I already mentioned, if a switch goes down, two different controllers will notice it at slightly different times, just because of physical properties of the network, signal propagation, and so forth. And so it's far more important that one of the controllers reacts instantly rather than waiting for consensus from the rest of the group. And so the idea here is that the information is also accessed from everywhere, so it needs to be cached and distributed entirely, so it cannot be sharded. Because if the topology state is partitioned, then algorithms which need to have the entire views of the graph the topology graph now become bottlenecked by having to access information from peers. So this stuff is read very, very often. It's updated also reasonably often, especially as you have a large network. You are increasing the likelihood of having events like go up, go down. I mean, even if you were to ask Google in their very well-behaved data centers, they're still dealing with network anomalies owing to frequent events due to port outages or link outages. So it's written often, read definitely very, very often, and generally it's you require a holistic view, and so and it's accessed everywhere. So you know, but in real life, of course, you have ONOS cluster has multiple physical nodes. Not all of those nodes clearly should be engaged in conversation with every switch. So generally, they're going to be talking to a portion of the environment. So each of them have a direct view of only portion of the environment, right? But they need to form collectively a single mental picture of the entire network. Of course, that picture has to lie somewhere. It's just not sitting there in the ether somewhere, right? So the picture has to be distributed and locally accessible from every single cluster. That's what I was talking about. Now that presents an interesting dilemma. You know, because you may get something may happen over here, and which is, let's say, connected to this machine, and the event needs to propagate over there. But you, for example, if both this and this node are connected to this switch, they will both see that event, but perhaps at slightly different times. And so the merging the state, the topology state, becomes an interesting problem, because not only you're seeing the switch links events to topology events, essentially they are graph operations, right? You see those coming from the environment, but you also get potentially simultaneous or potentially slightly out of order notifications from the peers about those same events. And so if you imagine a scenario where you have a link flow, link up, link down, link up, it is very important that you arrive at the correct final state, because if for some reason you were to switch order of events and you interpret it as a link down, a link up, link down, and, link up, and link down, you might end up in a wrong final state. So it's important that you treat with them, that you figure out whether this notification or that notification should bear authority. And so if you were to look at it closely, why that is, you're going to have a switch that's controlled by two machines. Generally, it should be, right, in the case to support loss of a single controller, at least two. One of them is going to be crowned to be the leader or master of the device. And then, of course, if you were to apply the same strategy, then you have sort of a picture like this, where you have a primary relationship represented by solid line and backup relationship represented by dash line. So this is sort of a mental picture that's formed of the Mastership matrix. Now, if something happens to one of the nodes, there will be one or more switches that are going to be affected by this, and some other node needs to be crowned the master, at least provisionally, and potentially others need to be nominated as backup. So that's what happens in the environment. That's what we would like to have in the control plane as well. Well, but what happens is, for example, if I'm probably going a little bit out of order here. Let me skip through. Okay. I'm trying to save for time here. So let's say that switch is elected as master. A particular node is elected as a master of a switch. And we have a particular state E replicated throughout the cluster. Now, in the case of failure, now we arrive at state F, where basically the same switch is now mastered by a different controller. And then a notification comes to another member in the cluster. And so he now needs to be able to reconcile what is real. Is that the ONO Mastership information the Mastership information? So the scheme that we use for this, so in order for us to be able to deal with this sort of chaotic influx of events, we at least need to somewhat establish some partial order for these events. And so the strategy that we use for it is basically we could use a strongly consistent store, but you can't do that for every change in the network. I already illustrated that that would be very poor performance and bad choice. So to partially order it, we track basically the mastership changes. So if a master changes, we start a new epoch, and within that epoch, all the events are going to be serialized within that epoch. So there's a major coordinate, which is the term number, and minor coordinate, which is the sequence number. And so all of the messages, topology event messages, are essentially signed with this two-part block: mastership term and sequence number. And the sequence number switch, which since it's tied, the mastership term switch, which is tied to the change in mastership, is propagated in a strongly consistent fashion. So everybody agrees, all the nodes agrees that we are on a new, in a new epoch, and we are going to be using a new term number for all the subsequent events. But from that point onward, at least until mastership changes again, all of the topology messages emanated from a specific host, from a specific controller node, are going to be sequenced using a locally issued sequence number from the master. So basically think of it as like a century and years within a century. So the consistent swap over happens only every century, which we can afford, that's okay. But then the individual events within that century are going to be strictly sequenced within that epoch. So you're gonna come basically with sequence of events, something like this, And this is of course relative to each device. And so any port events or device events, and also link events, because links are sourced or targeted at certain device, are going to be sequenced by essentially the mastership. So this is sort of an illustration. So if you have epoch 1 where, let's say, a device was mastered by first node, and then epoch 2 where same device is now mastered by another node, you have these separate epochs. And then within that, the sequence numbers are going to be mutated only within the context of a certain master. So this allows us to achieve partial ordering of topology events, and that's basically what we're after. So you can see that it's a three-part. It's relative to each switch, as I said. So it's basically a three-part vector of switch identifier, the term number, and then event number issued locally in the context of the master of that switch. So if you were to replay the sequence of events, here you can see that event are propagated. And so then if you have a mastership change, you can easily reconcile which event should carry authority. So for switch 1, clearly the second term wins over the prior. That allows the observer node to arrive at the proper state. So it's essentially treated as the topology information is essentially treated as a state machine that's driven by partially ordered events. So that's just an example of how we treat topology, and it's an example, where each instance has a full copy because it's needed very often, and the events are timestamped properly. Still events are discarded, and this is how we use to drive the state machine to keep arriving at the same picture. Of course, you could have a condition where, for example, node goes out for an extended period of time, and so he loses events. So then you wonder, okay, what's going to happen, right? how do they eventually converge on the same picture? Because if it's a state machine driven by events which are partially ordered, if you lost entire sequences of events, you now lost the data that's going to drive the state machine, and so you have entropy entering the system, and that's bad. Basically, it prevents you from ever converging. And to avoid this, because it's a real possibility, and I don't think it's an avoidable one, ONOS uses, to be able to deal with drop messages, ONOS uses essentially gossip-based anti-entropy. This is Madan's illustration here. So basically where you have the two nodes periodically get together and they discuss things. They just ask each other, hey, have you heard about this? And the other one says, no, I didn't. And that is usually a signal saying, okay, give me, and basically he can ask for an entire fresh copy. So we have basically a mechanism through which we can detect that a node has drifted apart from the pack, and it can be resynchronized. So basically, the nodes randomly engage in pairwise conversations and exchange information with each other. One benefit of this is clearly it's very lightweight, because the question about have you engaged, have you heard about this? It happens only periodically. It's not timeline. It's timeline-wise. It's not associated with any specific events. So it doesn't actually delay processing of any specific topology events. It happens in the background. And it's peer-to-peer. So generally, if you have a node, because the information is propagated everywhere, usually asking one node is good enough. You're going to get the picture. So in our measurements, actually, the convergence is extremely fast. And it's very, very lightweight. And of course, one benefit in the context of dynamic configuration, when you configure a new node into the cluster, he can come to speed very, very quickly, because he uses the same mechanism to come up to speed. So this is sort of an observation here. Yeah. I mentioned a view should be consistent with the truth, which is where the network lies, rather than with other views. And eventually, the views should agree with each other, of course, too. And this is where anti-entropy comes. So, since we're observing the real environment where events happen, whether we control them or not, this sort of a strategy using eventual consistency is the best option, best choice. So all of this is hidden inside eventually consistent map, all of this stuff. So from a consumer's or application standpoint, they don't have to do any of this. They just simply say, I have state that can be treated in an eventually consistent fashion that's good enough for me. All they need to do is build one of these maps using one of our factory methods, and poof, they have a primitive that they can use to back their store. So their stores can actually be very, very simple. They just need to implement the high-level abstraction semantics and project those onto one or more of these underlying structures. You can also, of course, you don't have to use the two-part clocks like I described, but you can also provide your own alternate clocks, which, of course, someone have to provide some partial ordering scheme. Okay, so what about flow state? That's an example of a consistent state treatment, specifically using master and backup strategy. So I've already mentioned that the device is mastered by one node, and so the flow state follows that, and essentially makes sure that that master has gets a copy as part of the mastership. The flow authoritative copy of the flow is established on that node. And also a backup is made, if there is one already, to make sure that there's a failover, place to failover. But it's not necessary for all of the nodes. There may be some nodes in a cluster that know nothing about the flows for the device. It's not necessary. There's the other examples of control plane, for example, like resource allocations, intents, or other application generated state. And clearly, for those For those cases, they may or may not choose to use consistency or eventual consistency. They can figure out what they decide to do. So here, since these slides are for like a 2-hour talk, I'm going to cherry pick through of these because rather than trying to go blind through these. Are we doing on time? What?
Pretty much done.
Okay, so let me just summarize really quickly here. So applications, most subsystems in ONOS don't expose their stores directly for others to write to. The stores can be thought of as a sidekick. So and applications should be built, in our view, applications should be built following the same pattern. Most of the subsystems in ONOS export interface. Basically, they export interfaces for other components or for their for applications. Often those interfaces are set up in both asynchronous and asynchronous fashion, where application can come in and through request response can simply query and get state from the core, or they can add listeners and basically act as observers on changing state. So that's from an application standpoint. They interact with the service. In some cases, there may be privileged functions that are separated into a parallel administrative service. And all of this is implemented by a manager component. Of course, some components, like for example, especially the ones dealing with environment directly, like flow programming or device and link and host discovery, I have also southern components, which use, this is where the provider pattern emerges. But I don't want to talk about that necessarily right now. The key part I want to focus on is the separation of responsibilities between the manager and the store. We've established a pattern from the very, very first release of ONOS, where the division, where the manager component is responsible for managing mostly the north-south type flows of information. And it's completely devoid of any east-west. That functionality and persistence, that responsibility is delegated to the store. So the store is the one who is responsible for persisting and synchronizing the information across. And this is where the complexity is completely absorbed. And this is where the use of the primitives occurs. And so it's a key attribute of the architecture, is the separation of the north to south and east to west type flows. So just to summarize, so the ONOS architecture, so the platform architecture is distributed. It's a cluster of instances, symmetric, where all the nodes are the same. That doesn't mean they have to process the same information, but they are equipped to process the same information. It's fault tolerant in the sense that the cluster can remain operational in the face of failures. It's locationally transparent, where you can execute logic here as you can anywhere, and it doesn't really matter. Of course, performance could be affected, but that's that should be transparent. And it's dynamic in the sense that you can adjust the size of the cluster at runtime to account for different changing environments. Nothing but that. I think 30 minutes ran out right now. So I realized I rushed through some of these things a little bit. Sorry, just shut this off. I realized I rushed a little bit out of sequence through some of the information, but there's lots of information to cover, and I want to make sure I touch on some of the key points. So hopefully, is there time for questions in the schedule? I don't know.
Just a couple of questions, maybe.
So what are the parameters on which the Mastership collection will be? Because it have 3 different instances of ONOS running. So.
Good question. So in absence of outside information, it will be fairly random. Usually, it ends up being the node which is switch over. Yes. Yes. Okay. Usually, the first node that gets contacted by a device or that reaches out and contacts the device, usually the first one who asks is going to get the mastership, generally. Of course, you can force rebalancing, so you can control, you can actually select nodes and assign them to specific masters, so it can be manually affected. But we also have a notion of region, which is basically a set of devices which share the same mastership and backup slave chain. So, and the regions are intended to be able to control affinity of devices to controllers in a geographically distributed context. So you can actually affect it using the region configuration. Hopefully that answers your question.
Okay. And I think that on the note.
Okay, thanks.
And if anybody has any more questions, I mean, you can find Tom around and ask him offline.